So given a joint probability mass function, we can find the expected value in the usual way, sum the products of the payoffs and the probabilities. We just need to take into account all relevant probabilities. For example, suppose we have a table of values, and we want to find the expected value of x, of y, and of x plus y. So for that, we'll need our probability that x is any one of its possible values, 1, 2, or 3. So for the probability that x equals 1, those are the probabilities of all our possible outcomes where x equals 1 and y equals whatever it is. And so those will be, and we find for x equal 2, the outcomes that have x equal 2 are, and those probabilities give us, and for x equals 3, the outcomes that give us x equal to 3 are with probability. And we can use those to compute our expected value of x. So for y, it could be 0, but it doesn't really matter because that's going to be multiplied by 0. And the outcomes corresponding where y is 1 will be with probabilities. And so our expected value of y will be. Now for the sum, since x is 1, 2, or 3, and y is 0 or 1, then the sum is going to be in, and so we can find those probabilities. So to find the probability that x plus y is equal to 1, the only possibility there is that x is 1 and y is 1, and so that will be, if x plus y equals 2, this event can be, and so those probabilities are, and we get, if x plus y is 3, this can be caused by the outcomes, and so our probabilities are, and finally, if x plus y equals 4, the only way we can do that is if x equals 3 and y equals 1. And we can do a quick check here. All of the possible outcomes are listed, and so our probability should add to 1. And so we can compute our expected value, which is the sum of the values times the probabilities. And that will be, and likewise, if we have a function that gives us our probabilities, so we can find our expected value of x, y, and the sum. So we find the probability that x equals 0. Well, who cares? It's going to be multiplied by 0. The probability that x equals 1, well, that will occur if x is 1, y is 0, or if x is 1, y is 1. And so those probabilities are, if x equals 2, the outcomes that lead to that event are, and so our probability is, and for x equals 3, we find, and that allows us to compute the expected value. If y is 1, the outcomes that make up that event are, and so we find, and again, the probability that y equals 0 doesn't matter since it'll be multiplied by 0. And so our expected value of y is, and again, we note that x plus y is 1 of, and so the probability that x plus y is 0 is, and that doesn't matter anyway because we'll be multiplying that by 0. If x plus y equals 1, the outcomes that make up that event are, and so we find, if x plus y equals 2, the outcomes that make up that event. X plus y equals 3, the outcomes that make up that event. X plus y equals 4, the outcomes that make up that event. And that gives us our expected value. And, as before, given a joint probability mass function, we can find a joint expectation as long as we can properly account for all outcomes that produce a given payoff. This means we can also find the variance of the random variables. So going back to our table, we've already found the expected value of x, and since we already know those probabilities, the expected value of x squared will be, and that gives us our variance. Likewise, we already know the expected value of y. The expected value of y squared will be, and so we can then compute our variance. As for the sum, we've already found those probabilities, and so we already found the expected value of the sum, and to get the expected value of the x plus y squared, we find and that gives us our variance. And again, if we have a formula that gives us our probabilities, we can find the expected value of x squared and the variance. The expected value of y squared and the variance. And finally, the variance of the sum. And at this point, note that in the first example, we found the expected value of x, y, and the expected value of their sum, and the expected value of the sum was the sum of the expected values. But we also computed the variance of x, y, and the sum, and the variance was not the sum of the variances. Likewise, we saw in the second example, the expected value of x and y did give us the expected value of the sum, but again, the variance of x and y did not add to the variance of the sum. And so the natural question to ask is there any relationship between the variance of x, y, and the variance of the sum? We'll take a closer look at that later as we explore more about expected value.